Hello everyone. So we're going to move into this section number 2 in unit 2. So in this section, we are planning to discuss about chapter 6 in your textbook. Especially we're going to talk about two important concepts. One is the centripetal force and the other one is the universal gravitational acceleration. So now you remember that what we discussed in earlier chapter. We discussed about many forces. What are the forces we discussed? We discussed about the applied force. If you apply push or pull, that will be the applied force that will move the object. And then we discuss about the force of gravity. Force of gravity is a force that act for the object straight downward direction that will be able to calculate by using mass time gravitational acceleration. So now, next we move into the tension force. If you drag the object by using the cord or the thread, there is a force. That force we call it as the force of tension. And if there is an object sitting on the any kind of table or any contact surface, there is a force perpendicular to the surface. That force we call it as the normal force. And also we talk about the friction force. If there is object moving on the surface, because of these two surfaces microscopic pattern on the surface, there is a force friction that will be acting opposite direction to the motion. If object moving this way, friction force will be this way parallel to the surface. In addition to that, are there any other forces that we need to talk about? That's what in this chapter focus in. This chapter we're going to focus into the centripetal force. That means if there is an object moving on a circle like this object has a force towards the center. That force we call it as the centripetal force. And in addition to that, if there is a two objects sitting in some distance, these two objects has the attraction. That attraction force is coming from gravitational attraction. That especially when these two objects are on the earth, there is a small gravitational attraction that we can ignore. But when you go to the planetary system, because those are astronomical units, very big masses, very astronomical units is longer distance, then your gravitational force will be stronger in that case. So those are the things that we're going to discuss in this chapter. Let me share the screen first. Okay, so now the chapter that we working with chapter 6, right? And in your unit number 2. So now let's go into the your presentation. Okay, so now under this section, I am planning to discuss about circular motion. Circular motion is object moving on a circle, and that motion can be a uniform circular motion or it can be a non-uniform circular motion. In your class, we're going to focus into uniform circular motion. And then later, we're going to jump into the Newtonian's universal gravitational law, and then a little bit about the Kepler's law of planetary motion and a little bit about the satellite motion. Those will be the plan for the section. So now in circular motion, when there is an object moving on a circle, that object in real life, that object keep changing the velocity. That velocity that keep changing on the circle, we call it as tangential velocity, right? So now this is the tangential velocity on the circle. If it is keep changing, we call it as non-uniform. If it is a constant velocity keep rotating, that is called it as uniform circular motion. In your class, we mostly focus into uniform circular motion, although in real life problem, they are non-uniform. Okay, so now there is a velocity on the circle tangential direction. Because of that change in velocity gives us an acceleration towards the tangential direction. Now if it is uniform, tangential acceleration is 0, but we already know those things. Only thing that we're going to focus in, when there is an object moving on a circle, that object has the acceleration towards the center. That acceleration we call it as centripetal acceleration. So if there is acceleration according to Newton's law, there should be a force, because net force equal mass time acceleration. Now, if there is centripetal acceleration, there should be a centripetal force. That is the centripetal force that we are discussing. Now, it is very important that centripetal force is not something that we have as an additional force. That is the force in that situation. Depend on the situation, that force can be a different forces. But that force towards the center altogether, we call it as the centripetal force. Okay. So now if I have a chord attached to the object, and if I'm going to rotate this object on the circle, since there is a thread, this thread has the tension force, then that will be the centripetal force, that will be exactly the tension force. If you take a turn on your vehicle, when you take the ramp, then there is a force toward the center, that will be friction force at that time, right? So it depends on the situation. The experiment that you're going to do in the class, in the laboratory, that will be the spring force. So according to the problem, your centripetal force can be anything, that the force towards the center. So now, as I mentioned earlier, this velocity, if velocity is keep constant throughout the problem, we call it as the constant velocity or uniform circular motion. So now this force or the acceleration that I'm talking will be able to derive by using simple geometry, but we are not going to do it. I'm directly going to use it. So centripetal acceleration can be calculated by using tangential velocity squared divided by the radius of the circle. After you know that, if you multiply that times mass, you will be able to get the centripetal force. So now, in addition to that, we're going to learn those things later also, the period of the oscillation, so period of the circular motion. Simple example is, if you take a circle, you start from this place, and if you go around this circle and come back to the same place, you are complete in one cycle. That if you take the timer and measure the time for that cycle, we call it as a period in seconds, measured by using seconds, right? So now, if this object has the speed v, it travel the distance of circumference of this circle, that is the 2 pi r, divide by the time it will take, then you will be able to calculate the velocity, right? It's really simple calculation. So now, there are many examples of centripetal, but I just need to mention about this highway banks, road and unbanked road. So when you take the ramp, you will see the bank road or you will see the unbanked road. Bank road means it is a inclined shape ramp, and unbanked means they are flat ramps. So now if you take the flat one, right, flat one, so now the view that you will see is your vehicle is here, it will take a circular pattern, this is the center, so this going to basically have a force that act toward the center. In this case, it is a friction force, static friction. Never ever draw the centripetal force on the free body diagram. Centripetal force is not a force in the free body diagram, that is coming because of the acceleration. So now if you write my Newton's law toward the center, F equal mass time acceleration towards the center, now my mass is m, and the acceleration toward the center will be mv square over r. So now this will be going to compute as mv square over r, and this will be your centripetal force. Now if the centripetal force is friction force, then this will be it, right? So now if you take the friction force, we know that in this case it is actually static friction, not the kinetic friction. Vehicle is moving this way, your kinetic friction will be this way, but I'm talking about the friction that I have toward the center. That will be static friction, will be static coefficient times the normal force. We know that normal force will be just a weight of this car, will say mass times g. So now if I combine these two together, what will happen is mu smg is equal mv square over r. Then m will cancel out, and then you see v will be equal to mu S, G, and R and root of that. So that means this is the maximum velocity that your car can have when it make an unbanked turn, right? It is mass independent, but it depends on the GR and the static friction. So now this is what happening in there. So now that your roads are not always unbanked, your roads can be a bank road. Now it's very important that if it is a bank road, your vehicle actually will do a turn without the turn very smoothly, even without the friction. That's what I say. I'm not going to derive any equation, but what will happen is in here, you see that the center is here. This is where your center is, but there is a pose toward the center because of this normal pose. Now, normal pose component Fn of sine theta will be to the center. That means your centripetal force will be coming from the normal pose even without the friction. That means we can have a turn on the bank road even without the friction. Okay. Okay, good. So now non-uniform circular motion. As we mentioned, non-uniform means you have basically tangential acceleration. That means velocity to the tangent direction is keep change, right? So simple example you can think is the loop, right? This guy can maintain a circle. How he maintain the circle? If you go on the bottom in here, you definitely have a normal force and force of gravity. If you go here, you have normal and force of gravity. If you go here, normal and force of gravity all lie straight down. Then this object cannot actually stay in here, it's going to fall down. But he's not. Why? Because he going to increase the velocity when it come to closer to here, and then that velocity is good enough for him to jump that turning point. Then he can go on the circular uh, surface. Okay, that is non-uniform circular motion. Okay, so now let's move into the Newton's law of universal gravitation. So Newton developed three laws that we discussed in earlier section, but this Newton law is totally different from those three. Okay, so Newton's think about how the planetary system, how the planets moving around the sun, right? Then because of that observation, he want to realize that they are keep in orbital motion without attracting them together or without going apart from each other. So now this keep in this orbital should have some connection between these two objects. Then that's why actually we have force of gravity, because you have attraction toward the center of the earth. That's what we define it as force of gravity, right? If there is an object, there is attraction between these two. That is the force of gravity or gravitational force for that object. Okay, similar thing. So now this gravitational force will be able to calculate by using this formula. That's what the Newton's found. The G is a constant. We call it as universal gravitational constant. It is not the lowercase g that we discuss, right? So now this force is attraction force, equal and opposite on the two objects, and depend on both masses and depend on the distance between these two masses. They are far away, their force is smaller. When they are close together, their force is greater, right? So now connection between this lowercase g and uppercase g is coming from this phenomenon, because when you are on the earth, you are the object. Then you have a force towards the center of the earth, that is the force of gravity that we already know, it is mg. Now that means this object has the force. That force, I have it on left side, will be just mg, and right side, this is the mass of you, and there is a mass of the earth. Because of that m and me, and this is the radius of the earth, right? Then you have a connection of g and uppercase g. So now this equation will explain a lot of things that we discussed earlier. The g constant, lowercase g, we call it as gravitational acceleration, that is 9.80. But is that constant for everywhere? No, because it is depend on the RE. That means if you go to the mountain area in Denver, then you have the RE is greater than the New York area. Because of that, your gravitational attraction in the Denver will be smaller than the New York, right? So those are the numbers that you can see. This is the New York value, this is the Denver value, right? And also there is another thing in here. You see that the gravitational, this G value is different in closer to the equator and North Pole. There is also a reason for that. Here, if you know that Earth is spinning itself, that means this person is keep rotating, but this person is almost at rest. Because of spinning, there is a centripetal force acting on this direction. Because of that, it will reduce the force of normal force on that object. So that will give you the little weight less than the other one. Because of that, G is smaller, right? So now according to the Newton's law, F is proportional to 1 over R squared when you go outside, right? But inside, actually, this G is proportional to the R that we are not going to derive it, but that's how it will work inside the Earth, okay? Okay, so now we're going to move into the weight and weightlessness. So weightlessness means basically no support force or free fall. Or you can say that it is a complete absence of the sensation of the weight. We call it as the weightlessness. So this is very easy to understand by using your elevator problem. Okay, so now we'll say you bring the balance to the elevator. You're going to stand on that. You're going to measure your weight on the balance. So now when we come to when the elevator is rest, you have force of gravity equal to normal force. That means your elevator read exactly same weight as you have in real outside the elevator, right? So now in this case, your elevator going upward direction. So now you have definitely force of gravity and normal force. But are they the same? That's the question. You need to use Newton's second law and see what will happen. Then your normal force will be, in this case, your gravity force will be basically greater than your normal weight. So what that means is if you write the Newton's second law towards your y direction, this is y direction, you have force of normal and Fg is downward direction. That should be equal to mass time acceleration upward. You see that your normal force in this case will be Fg plus n. That means basically it's greater than your usual weight. Do the same for elevator going downward direction. Then you will see your Fn is actually your mg, and it will be less than the mg. That means Fg minus mg in this case, it is less than. But in any case, if it break down, then you will see zero force. Why zero in this case? Because this is going down with the G value. Then you have normal force minus Fg equal m and g in negative. Since Fg equal to that, your Fn will be equal negative mg plus Fg. So Fg is mg. Because of that, this will going to cancel out. Then your Fn will be 0. That is what weightlessness means. Okay, you're going to do exactly same problem in different categories in your recitation session. Okay, so now let's move into the Kepler's law of planetary motion. So Kepler developed a lot of things and discovered a lot of things, but most famous thing is his three Kepler's law that will related to the planetary motion. So one of the important thing that he discussed is planet is not moving on a circular path, it is moving on an elliptical path. So now according to that, he discussed about these three laws. Okay, so what is the first law is? First law is saying that any planet on the universe in our Milky Way galaxy, all the planets are moving around the sun on the elliptical path. That's the first one, by keeping sun as focus. And then second law is saying that if you take a time that planet is moving from one place to another, if you take the time and if the planet moving from one place to another with the same time interval, if you take these two areas will be equal to each other. That is the second law of Kepler's. Third law is very important law. Third law is saying that if you take the squared of the orbital period of the planet is directly proportional to the cubic of the distance, the average distance between sun and the planet. So that means t squared is proportional to the a cube. This k is the basically 1 over k or k, sometimes called it as Kepler constant. But this k value, according to the Kepler, it is just 1. Because the Newton is the one that who combined Newton's gravitational law to the Kepler's law and then found that k equal actually this number. That means the Kepler's third law you can use not only for the planet moving around the sun, we can use it for the planet moving around the planet or any other orbital motion if you use your m is mass of the orbit. Okay, so that's the combination of the Newton's and Kepler's law. Okay, so as I mentioned, k is equal as Kepler found because he used the astronomical unit for the distance and time as the Earth years, that is 365 days, and mass as solar mass. So that's why k equal 1. Other than that, k is not 1. Okay, so now here I am plotting the a cube as a function of t to the power 2. That will be just a linear plot. Okay. Okay, satellites in circular motion. So now we know that the satellites is moving around the Earth surface, closer to the Earth's surface, but not the exactly radius of the Earth. So now if I know the distance from here to here, that will be basically RE times the rest, right? So then this object or satellite has the force, that is the centripetal force, as we know, will be equal to mv square over r. Then by equaling this into your gravitational force, you will be able to find it out, the velocity. So now you can say what velocity should travel to keep in 24 hours when it go around the Earth. If you need the period 24 hours, what velocity should it travel according to the distance you're going to set up your satellite. Okay, so that will be should be calculated before you set up in there, because we need 24-hour rotation of the satellite around the Earth. Okay, so now that's it for this chapter.